This is Pre-Calculus section 2.5 on the fundamental theorem of algebra. And the key thing that we need to know about the fundamental theorem of algebra is that the number of solutions for a polynomial equation is determined by the largest degree. That's how we know how many solutions are going to be. And that includes both real and imaginary solutions. So not every solution is going to be real. We'll notice that as we look on the graphs for different things. But the largest degree is how we know how many solutions that we're going to have. Let's take that and go right into an example. So we have this equation. We want to find all of the zeros for this one. And since we know it's x to the fourth, this should be 4 solutions. And I'm going to help you out a little bit on this one. If you enter it into your graphing calculator like this, we could then go to the table to look to see if there's any solutions. I'll tell you right now that there aren't going to be any that show up initially. However, since the leading coefficient is 12, that means that if we go to table setup, I want the table start to be at 0, but the delta table to be set to 1/12, because we could have any fraction which has a denominator of 12 or any factor of 12. So we might get a 1/12, a 1/6, a 1/4, a 1/3, a 1/2. We have a lot of potential fraction answers. So I'd enter this equation in, go to my calculator. After I've looked at the integers and verified that there's none, change delta table to 1/12, and then some are going to show up. So then if I scroll down the graphing calculator, I would see that at x equals 2.33333, which represents 2 1/3 or 7/3, there is a 0. I could look on the graphing calculator, the graphing part of it, to see that there is an x-intercept right around that value. And also there's going to be a 0 at -9/4. Again, I could get that off of my table, verify it by looking at the graph. I know there's supposed to be a total of 4, but even when I look on the graph, there's only 2 x-intercepts on there. There should be 2 more solutions. What this means to me is either those 2 solutions are very far to the right and the left that they don't show up in my window, or perhaps they're imaginary. Because I have 2 solutions and it's x to the fourth, we can do synthetic division on this to simplify that equation all the way down to a quadratic. I'm going to pause this and do that work off screen. Synthetic division, we can simplify using 7/3, using -9/4, verify that they work, and we're left with these coefficients, which would give us 12x squared plus 0x plus 192 equals 0. One thing I notice is that I can divide both of these terms by 12. It gives us x squared plus 16 equals 0. Subtract 16 from both sides, then take the square root. So then we would have positive and -4i. So our 4 solutions, and we knew we were supposed to get 4, include 2 real numbers as well as positive 4i and -4i. As a reminder, those those imaginary numbers are never going to show up on your graphing calculator, either on the table or on the graph. We have this equation equal to 0. We're trying to find the zeros for this one. If you enter this equation into your graphing calculator, go to the table, you'll see that there is a solution at x equals 1. But that's the only thing you can find. There's no fraction answers because the leading coefficient is 1. You could check +1, -1, +5, -5. Those are the only potential rational roots to this one. If you look at the graph, though, that gives you another hint about this one. When x equals 1, you have a bounce point. So that means that x equals 1, we believe, is a double root. We can verify that with using synthetic division, and I'll do that off screen again. X equals 1, it worked twice with synthetic division, so it was in fact a double root because of that bounce point. That gives us this equation of 1x squared plus 0x minus 5 equals 0. So then if we solve that, we'd have x squared equals 5, take the square root, x equals plus or minus square root of 5. Those numbers are also showing up in your calculator as approximately 2 point something. They are real, they will show up. They're just not rational, and that's why they didn't show up on the table. But what we knew is that there were 4 solutions, and there they are. Here's our next equation that we're trying to solve. Enter this into your graphing calculator. The last term is -72, so there are potential integer answers of any of the factors of 72, which there are a lot. And they could be over the leading coefficient of 2, so we might have some fractions. And what I'll tell you is that as you look on the graphing calculator, you'll see that there are some x-intercepts. If you look on the table, you'll see that there is a 0 at -1/2. So to simplify this equation, we're going to take -1/2 and run it through synthetic division. We get down to this red equation, which isn't x to the 5th, but x to the 4th anymore. It represents 2x to the 4th plus 0x cubed plus 2x squared plus 0x minus 144 equals 0. It is a quartic. We don't have a quartic function like we have a quadratic function or quadratic equation, but it does meet a nice pattern. It's an equation that needs to be solved. I would divide everything by 2 to make it become 1x to the 4th plus 1x squared minus 72 equals 0. And while this isn't necessarily easy, it does look familiar to me. Off to the side here, if it were x squared plus x minus 72, I know I could factor that as x plus 9 times x minus 8. Those numbers multiply to -72. These numbers add up to 1. So this would factor that expression. I'm going to use that idea and apply it down here because it has the same coefficients and it has the same pattern. Instead of the degrees being 2, 1, and 0, now they are 4, 2, and 0. They're all doubled. So to factor this, it's going to be x squared plus 9 times x squared minus 8. It's using the idea of factoring number pairs to factor this. From here, we can go to the answers. If x squared plus 9 equals 0, then x squared equals -9. And if you take the square root of that, you get plus or minus 3i. Those numbers are not showing up even on the graph. And for the other part, x squared equals 8. So take the square root of that, you get plus or minus the square root of 8. That's plus or minus 2 root 2. Those decimals are showing up as x-intercepts on the graph. We have 5 answers, and then the 5th one is this -1/2. It was our lone rational root. So these are the 5 solutions to this one. We got 1 from the calculator and the other 4 by using that with synthetic division to simplify it down to get it into an equation that we can actually solve. Here's our next equation, or next expression actually, and we want to write this as a product of linear factors. So as we look at this expression, we might get to some integer answers that have, that'd be 3 or -3, 1 or -1. We might get some fractions with denominators of either 2 or 4. So if we enter it into the graphing calculator, we can find the integer answer of +3, and we can see the fraction answer of 1/4. Then, once we have those two, we can use synthetic division, simplify it down to get it to a quadratic, use quadratic formula to come up with those two solutions. Go ahead and try that. You can pause the video for now because I'm going to put those answers that we would get up here on the screen. And here they are. So these are the roots. The directions this time are different as I'm asking you to write this as a product of linear factors, meaning if we were to factor this one all out, it would be x minus 3, x minus 1/4, x minus 2 plus the square root of 5, and x minus 2 minus the square root of 5. So here it is as a product of linear factors. We're going to go a little further with this one. The x minus 3 is okay. The x minus 1/4, if I multiply both of those terms by 4, we would get 4x minus 1. Since I multiplied this by 4 on the inside to make them integers, I'm going to put a 1/4 here. I don't need that 1/4 because this 4 will take care of the 4 we have there. And then distribute this negative sign, it's x minus 2 minus the square root of 5, and then distribute this negative sign, x minus 2 plus the square root of 5. And here is the original expression written out as a product of linear factors. How did I know to go from x minus 1/4 to 4x minus 1? Well, if I solve this, I get 1/4, and if I solve that one, I get 1/4 as well. So I'm just multiplying both of those terms by 4. This is now going to give us a leading coefficient of 4 like we have in the original problem. Corrections here say that this red graph is a function. It's a 5th degree polynomial, so it's x to the 5th or 3x to the 5th plus some other numbers in there, maybe 4x to the 5th or -x to the 5th. What we're supposed to find out is how many imaginary solutions does it have if this is the complete graph over the real numbers. For the first one, I see that there are 1, 2, 3 x-intercepts, which means that there are 3 real solutions, maybe Rational, maybe irrational, we don't know. But if there's 3 real solutions, that means that we're left with 2 that are imaginary. They're just never going to show up on a graph. They always come in pairs. There's always got to be an even number of them, sometimes 0. This time we have 2. And the next graph, I'm seeing only one x-intercept, which means that we must have 4 imaginary ones because they're just not showing up on the graph. In the third example, I see 1, 2, 3, 4, 5 real solutions, so there are 0 imaginary this time. Example 4 has 1 solution, 2 solutions. That leaves 3 for the imaginary, which isn't possible. Imaginaries always have to come in pairs or complex conjugates, so this doesn't represent just 3 solutions. I need to recognize that this is also a bounce point, so as I'm counting, we have 1, 2, 3 that are real, which means that there are still 2 imaginary ones that are out there. And for the last one, I'm seeing the graph look like this. This point is sometimes hard to determine, but it's not just one solution. It's not a bounce point. Like if I were to continue this, it's kind of like half of a bounce point going in that direction. And it's also kind of like half of a bounce point going in that direction. We call that a point of inflection. That means that this is a triple root. It stands for 3 solutions. So that means that there are still 2 imaginary that are out there. Again, they're kind of hard to identify. So if I actually had numbers, I could go to the graphing calculator, get this value, use synthetic division once, twice, 3 times to simplify it all the way down to a quadratic.